Good morning, mathematicians. We're coming to the end of the week, so hopefully in chat today you'll be telling me about all the crazy proofs that you got done. All thanks to the things you learned on this channel, no doubt. We got a new sheaf video having dropped. And today there's yet another video, start of a new series, because OneNote has updates. Yes, continue for free. Oh my god, it scared me for a second. Thought I had to pay for something. Oh, Deepak. In time for nightly ASMR. Good to hear, good to hear. Quality. Wow, so a new the quality Edit Smith feud has a new player. Well, not a new player, but Deepak's been in these office hours for a while. But new competition for first in chat, I see. I do actually have an idea of something I want to yap about today, if there aren't questions, or until there are questions. Hello, Morphisms. Nice. Great name. Welcome to the office hour. I kind of want to see. I do have some plans for what to yap about if there aren't too many viewer questions. But let's take a look. Oh, you're an experienced yapper by now too. Good. That's what I'm really after here. Trying to just make everyone better at yapping. Yeah. You think you do deserve some credit? That's true. 7 a.m. flat. Damn. Yeah, 100% you deserve credit. But I mean, Deepak did beat you to it today. But you're on it. You're definitely up there. I wonder if I should keep track. I should keep track of the numbers. Perfect thing to watch at 4 a.m. Oh, okay, sweet. Yeah, I'm glad this is doing it at 4 a.m. I was about to say that I feel like, hey, did Reddit freeze for me here? What's going on? I was about to say that I feel like 4 a.m. watches are that's definitely the time to be watching something more abstract, or more definitely not more abstract, more niche. But what am I talking about? There's like, my channel's tiny. This it is the ideal 4 a.m. thing. Oh, 7:30 where you are, huh? Okay, let's see. Did it unfreeze? Okay, sweet. Current controversial mathematics? Okay, let's take a look at that. That could be cool. Can we talk about AI and how it's going to change how we do research? We can. I mean, probably if we talk about it a bunch, I'll put it in the title of this video and I'll get more views, probably. Actually, I don't know. The ones that I say AI in the title, I don't know if it's I don't know if they actually get that many more views. Can you ask an education related question? Yeah, go for it. Ask away. But maybe Deepak wants me to yap about AI a little bit first. Go ahead, put your question in chat. Yeah, I don't know. I mean, the thing is, no one knows how AI is gonna change research. My algebra student, there's a bunch of people who are very obviously using algebra, or using AI on their algebra assignments, and yeah, and it happened last semester too, and it's just so obvious. It's funny, but it's also like, well, I don't know. So one immediate thing. Speaking of education, I think one thing that is going to change right away is that we're going to go back to mostly exam focused, which is tragic because for a long time, I've said, or I've believed that if you're trying to be a mathematician, then really the best thing, like, it's good to have a course that's where most of the weight is on homework, and has like difficult assignments and has like projects and stuff, because that is more akin to the mathematical process, sitting with a problem for a long time and trying to be creative. So I always, yeah, I've sort of been in favor, both on the student end, and now I'm slowly evolving to the other end, and I still have these beliefs that that's where the weight should be in courses. But with AI, hi Jens, with AI, I don't know. It's kind of ruining it. I mean, on the one hand, it's so obvious that these students are using it. But like, I talked to one of the professors. I gotta talk to someone else. One of the professors in my department was like, "Oh, well, we can't really prove it, so there's nothing we can do." But then another prof in my department, I told them about AI found in their homework assignment, their students' homework assignment, and they're just like, "Yeah, give them 0. I'll talk to them." So, I don't know. Glad to see I'm alive again. Yeah, yeah. I die every Thursday. I'm not online on Thursdays. Actually, that's gonna change now, because I don't have my math help center hours now, so presumably I'll be doing office hours every day of the week, 7 days instead of 6. Seems that way. I didn't plan. I thought I would have too many commitment issues to be doing this, but it's been fun. It's now just part of my morning routine, so probably going to be like that. Basically, hitting on your question, you're an instructor, and we're trying to figure out how to assess students in the age of AI. Yeah, so yeah, I guess like I already said, the sad truth is, I feel that it's just going to have to be back to mostly exams, which is sad. I don't know. It's sad. Well, I guess it depends on your university's policy, right? So if it is true that it's hard for me to make these accusations against these students, because what the point that someone else brought up was that, like, it goes through the registrar or whatever, and like there's stuff that we would look at and go, oh, this is obviously AI slop, right? It's just very clearly, but maybe the registrar is not very familiar with what AI, specifically AI math answers, tend to look like. And and then also, like, with mathematics. Oh, okay, so you're teaching a coding course. I wonder if it's harder. Maybe it is as obvious to you, but I wonder if it's harder for you to detect AI or not in the coding, because with mathematics, I find there's a certain way that maybe I don't even want to say too much online, because I don't want to like tell students what if anyone's listening, I don't want to tell them the key hallmarks to fix. But there's like various obvious things in the like writing styles that it does, but that's it, like an artifact of, because it's giving you like, well, things with symbols, but an English language answer. So I wonder then, Alessandro, if it's as easy for you as as an experienced programmer. The main giveaway is that the variable names are great. There's good comments. Yeah, nice. Yeah. So I mean, there's a lot of hallmarks other than it just being good, but like, so one of the cases, so my Algebra 1 course, you expect people can write some mathematics, but the other course I found some AI slop in the other day while grading. It was like linear algebra 1, right? And so people have no idea how to write a proof, like they still, and most people in that class have no idea that proofs even exist, right? So they're just doing computation. Well, actually, this installment of the class under that instructor, she's been doing stuff to try and like get them ready to do proofs. Not quite proofs, but makes them try to put in like full sentences to explain their computation to get them used to this idea. But so clearly they have very little skill. I mean, some people are good at doing it, but it then makes it very obvious that when like an AI has gone in and like explained every sentence and it's all like grammatically correct and has that kind of feeling of typical math writing, and I'm like, oh yeah, come on, this you didn't do this. No one in this class is this good. On top of the other hallmarks, but the essay you mentioned is on Archive. Is mathematics obsolete? Well, let's take a look. Archive. Is mathematics obsolete? Cool. I'm gonna maybe skim this over. Yeah, hard to penalize for being too good. Yeah. But yeah, there's some cases where it's just like so clear. It's like no one at this level is submitting things like that. Like you're very obviously like, unless you're a super genius. But then guess what? you go look at how they do on tests, and oh, coincidentally, those are the students that score really terribly. Oh, shocking. Maybe they're a genius. Maybe they're a 1 in a million genius, and they also happen to like test really poorly. Happens. Well, it doesn't happen 20 times in a class. You need to make it sound like it was written by a dumb undergrad. Yeah. Claiming that math is solved because AI worked out some IMO problems. Is that true? Is anyone actually claiming that, though? I mean, this is you might jump to that conclusion from this provocative title, but I mean, I haven't read it yet. I don't know if you have, but you're doing your master's in Yang-Mills theory. Okay. Due to the nature of the subject, you struggle with the insecurity of not understanding every single proof completely. How do you deal with that insecurity? I don't. I just live in perpetual suffering, in constant shame that I don't understand every proof completely, and yet I trudge ahead boldly and continue trying to prove things, and here and there I backfill things when I can. But yeah, that's basically it. The thing is like, most probably it is just, yeah, I mean, it's good that you have the desire that you want to understand every proof. I mean, at some level we all, but I mean, we wouldn't be mathematicians otherwise. But yeah, at some point, like, you just have to, it's a hard point of knowing when you make that cutoff, and when you say like, yeah, okay, I just need to black box these things, because if I don't, I'll never get anything done. And then you go back and sometimes fill in those things. And I mean, that's one of the things I do with, like, my sheaf series video. Now these days in my research involves, like, equivariant derived categories of sheaves and whatever. That, I mean, that's not even that fancy in the grand scheme of things, but and trying to move ahead to, like, the categorical Langland stuff is like, yeah, I don't know, even crazier stuff, infinity categories of quasi-coherent sheaves and stacks and everything. And yet, I'm still going back and, through my sheaf series videos, or through my mentorship program that I've hosted at my university, it's, an excuse to go back and do some of these and fill in some of these more basic things in gritty detail. So, yeah. There's ways to justify to yourself when and why to go back and fill in those things. Struggle at the end of the day is part of learning and loving mathematics. Yeah. Yeah. Comment unrelated to the Avogadro paper. Oh, okay, I see. Yeah. Yeah. A little bit too much. Insecurity is why we do this, yeah. Trusting work of others is an important capacity for mathematics. Yeah. I don't know. It's hard, though, sometimes. Because sometimes there's, I don't know, very loosely written results out there. But, yeah. At the end of the day, it's all trust. It's all trust. But, of course, being able to recognize when one should be skeptical. Yeah. Yeah, so that's how it do be like. It is inevitable feeling small compared to the immensity of human knowledge, in this case, math. Yeah. Yeah, I mean, it's better than the opposite, though, right? Imagine like, exhausting all known things. It would get boring, you know? I mean, I don't like that I won't be able to know everything. Well, maybe I'll live forever, so in that case, I'd get to know everything I want to know about everything. Unless actually just the depth of knowledge keeps going infinitely deeper, and then it'll be a chase for all eternity. But I would prefer that to running out of stuff. I would prefer that to understanding everything. Just approaching godhood asymptotically. That's the ideal. Apologize if this post is slightly unusual, doesn't belong. I know people find Ooh, documentary filmmaker. Developing a film on a related topic. I have an interest in thinkers who challenge the orthodoxy, either by leading an unusual life, coming up with challenging theories. I've read a book discussing Alexander Grothendieck. Yeah, we need a Grothendieck documentary. Hi, Julie. We need. I've seen memes people have made about the mathematical extended universe. You know, now that there's like a Stephen Hawking movie and Oppenheimer and Ramanujan, John Nash as well. So yeah, we need we need the Alexander Grothendieck one. People like him still out there or a product of his time. Oh, interesting. Wow, top comment, Doran Zielberger. Yeah, very controversial. Yeah, have a good day, Alessandro. Pop by anytime. I'm happy to chat. Math, education, whatever. Oh yeah, Machizuki, definitely probably the most yeah. Paul Erdős led an unusual life. Is that true? Did he? Yeah, he didn't challenge the orthodoxy so much. There's a documentary of Erdős. Yeah, N is a number, I think. N is a number, I think it's called. So I remember watching that a long time ago. Yeah. Yeah, I mean, yeah, I think this post, though, is more about challenging the orthodoxy. It's not just being weird. I mean, every mathematician's a weirdo. Hate to break it to you. If this is your first time hearing it, chat, you're all a bunch of little weirdos. Me too, so don't worry. You're not alone, but sorry. Zala Films is probably the only one making quality math documentaries. Erdős, Zhang, Mirzakhani. Oh yeah, there's also the Mirzakhani documentary. Yeah. Yeah. Roger Penrose. Interesting. I don't know if he's so much... I mean, he's a little controversial actually because he like put some crazy ideas out there into the world. Um, but I also feel like people misrepresent him because he puts out like crazy ideas about like cyclic Big Bang cosmology, and everyone's like, "Oh, he's a crackpot," and here's why. Like the evidence contradicts his thing, but you know, he's not out here like some certain physics grifters, ex-physicist grifters, I would even say. You know, just making wild claims. You know, he at least my impression, what I remember from reading his books, is that he's always very careful to say, look, this is my idea. It is not the mainstream idea. I could be wrong. There are things we don't understand, and look, here are some alternatives to my idea. Yeah. Is he one of the greatest physicists ever? I don't know if that's actually true. I could be wrong. He's done amazing stuff. I'm actually not so intimately familiar with his actual research, but he's undoubtedly very talented in both mathematics and physics. And I would change the wording ever so slightly. I would say he's maybe one of the most important physicists ever. Of course, we can debate what does it mean to be a great physicist, but probably one thinks immediately of some sort of like important fundamental contribution to physics moving it forward. And in that sense, I think that there are perhaps a lot of people I would put ahead of Penrose in that regard. But I could be convinced otherwise. However, because of, well, exactly what I just said, the way that he treats his own ideas, and I mean, The Road to Reality is probably one of the greatest books, period, ever written. One of the most ambitious books. I mean, the goal is to try and take you from Pythagoras' theorem to string theory. And not in some, I mean, don't get me wrong, I'm about to say this, I'm not throwing any shade because I love these people, I've read their books, not in any sort of like, you know, Stephen Hawking, Sean Carroll, Brian Greene kind of way, in like 200 pages with like 3 equations. No, he gets down into it, into the nitty gritty equations. He tries to really take you along for the ride from a beginner to a string theorist, which is like not possible for you to actually just read that book cover to cover, understand everything, and then, oh, now I just get string theory. But I don't think anything of that breadth and scope has ever existed or will exist again for quite some time. That'd be a good thing to do a book club for too again. Okay. Well, let's yap a little bit about math. May as well. This is supposed to be an office hour after all. So here's what is going to yap about today. Is it, if I sit back, is the mic too far? Probably not. I think the sound quality is better when I lean forward, but it's like arching my back in a weird way. So, let's talk about, again, some stuff related to my research that I want to yap about a little. Probably, I don't know if we'll touch on it today, but I want to try and provide one motivation for affine Hecke algebras from my perspective. So if you happen to know some basic representation theory, you know, if I have a finite group G and I have some representation on some finite dimensional vector space, I can form the ring of functions. Well, it's called the group algebra, but we really just can formalize it as the ring of complex functions, complex valued functions on our group. This is then, given our representation, I can define a module. And how am I going to define that module? Well, I have a function. I'll have a function act. Maybe it's better to give an explicit. Let me just say that as a C vector space, this has a basis given by the characteristic functions, right? 1 sub g. And so what is the module action going to be? Well, I'm going to have the characteristic function 1 sub g act on v just via the representation, and then extend linearly. Right? So another way to say this, I guess, actually would be like a function f will act on v by summing up f g pi g v as we sum up over all of g. But if we treat this as just like a finite measure space, right? Just use the counting measure. And there's a reason why I'm rephrasing it like this. You'll see in a moment. This is just taking an integral over all of these values, dg. Okay. So and in particular, we care about this because this process actually provides for us an equivalence of categories between representations of G and modules over the group algebra. So we can go back and forth between these two worlds and prove things. So that's nice. We can use tools of module theory. So, how does this play into some of the things that I'd like to think about? Well, if we have now a group, p-adic group, let's say GLN-QP, or some other p-adic group, we can try and do the same thing, right? We have this study of representations, although we add these words, and these words are now going to be really important in what I'm about to say, although I won't define them unless you beg me to in chat. Smooth and admissible representations. And we would like to come up with some sort of analog of this story, although there's topology going on here, so probably just taking the full ring of functions isn't going to be useful. So what we end up doing is taking smooth functions, complex valued functions. So this ring C infinity, but this has nothing to do with derivatives. It's basically just that in the p-adic world and the complex world are basically just their topologies are very incompatible. So any attempt to make so basically all of our continuous functions into the complex numbers are just going to be, I guess I'm explaining one of these words, are just going to be locally constant. So by that I literally mean for all. Uh, what do I mean? I guess I mean for all G in G, there should exist an open set containing G. Uh, there should exist. No, it's the preimage. It's the preimage of a. Gosh, I'm confused about a basic definition in my own research. No, I'm pretty sure it's that the preimage of each point. So if F is in here, the preimage is an open set. No, that's all. That's a lie. It's locally constant. Yeah, for all G, there exists an open set such that F is such that F restricted to U is constant. Yeah, I got to drink more coffee, I guess. So, that's part of it. And now we might expect, we try and play this similar game before, right? So how are we going to, because now, okay, probably we're not going to add things up because there's probably like too many infinities. This group has infinitely many elements, right? So probably we're not going to add things up. But it's a locally compact topological group, so we've got this God-given measure on it, Gödel, God-L given measure on it, and so we can define, then if I had a function in there, we could define the action of a function on, say, say we had a representation, so that we again integrate over the whole group, and we just copy exactly what happens in the finite case. But okay, there's still things to worry about. We still don't know that this integral converges. So one thing that could guarantee convergence is actually if I go back here and I put a subscript C. So now I'm asking that these have compact support. So I'm going to now look at the ring of smooth functions of compact support. And now, I mean, you need to say something. You do need to use facts about like smooth plus. Is admissible really important here, actually? I do remember using that at some point, proving some basic things about these integrals, but yeah, maybe admissible gets used here, but you need to say a few things about why this is a well-defined notion and whatnot. Also, I didn't tell you. Why am I using F? I should use phi and psi. So how is this a ring? Well, we have it under addition. And you might wonder, well, what is the multiplication operation? It's not just ordinary multiplication, because, for example, when you look at this ring, the multiplication basically ends up being convolution. And that's, okay, maybe not surprising, because that's a thing that happens a lot in functional analysis. So if our operation is convolution, so convolution, and I always forget which side I want to put the things on as a G inverse X. I don't know. It matters, but not for our purposes right now. So under this operation, you can verify that this does in fact define a module. So there's a problem in mathematics is there's way too many things called Hecke algebras, in my opinion. There's millions. Okay, maybe not millions. There's many, 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 many things that are called Hecke algebras. Um, and this one, I don't think anyone calls it this, but sometimes I call this thing. So we use HG sometimes when we mean these smooth, compactly supported functions as a ring under convolution. We might call this the big Hecke algebra, or sometimes I call it the, what else do I call it? Sometimes I call it like the total Hecke algebra. Sometimes I say that. This is not standard terminology, but it's just because there's like 40 kinds of Hecke algebra that show up in my life. And it's true that we get an equivalence of categories. Well, there's some other qualifying words. It's like, what do we need to say? It's like non-degenerate modules or something. There's some special word there. It's like the admissible. It's like the admissible representations are equivalent to, I think, non-degenerate HG modules. Is that the term? I don't remember. But there's problems. First off, hello, Anubhav. Hello. There's problems. HG doesn't have a unity. So that kind of sucks. But here's what is true is that so I guess I do need to tell you what admissible means. So a representation being admissible means that for, again, you guys should be fact checking me on all of these things because I definitely misremember stuff all the time. And you should definitely go double check things I'm saying and read them in a book or something in case I said it wrong, because I definitely say things wrong. In fact, I said something wrong in my new sheaf video the other day. I don't know why I keep making this mistake. It's a weird habit I have that, and I know because I do this all the time. The sheafification is supposed to be a map from the disjoint union of stocks, such that S at X is in F sub X. But for some reason, I keep writing it as just a map into the product. Which, okay, a map that satisfies this, by the way, is the same thing as an element of the product. So, like, maybe that's why I'm getting confused, but yeah, it's annoying. It's annoying that I keep doing that. But I mean, everything I said in the video is still true. I don't use any essential fact of it being the product. I'm still psychologically thinking of it as a map from the open set into the disjoint union. So whatever. So just to finish this definition, if you're admissible for every compact open, the k fixed points of your representation has finite dimension. Okay, and so if we do this, it turns out that actually for each... let's focus now. Okay. Well, you're taking your nighttime ASMR very seriously, Deepak. For each of these compact open subgroups, we can create an idempotent element, E sub k, and actually, yeah, forget about that. That's important, but rather we can form instead this ring of bi-invariant. So this will be things in in this Hecke algebra such that f k1 g k2 is fg. So this is now bi-invariant functions. And now, so this smaller ring, it turns out this ring does have unity. So you can define an identity, which, okay, it turns out you build it out of these idempotents. So we can sort of shrink things down, and we know the admissible assumption, basically says, okay, well, I guess that gives us the like finite dimensionality of modules, but the idea is that somehow you should, if you restrict basically to representations which are generated by their k-fixed components, then you can study that subcategory by studying modules over this ring, and now you're studying modules over a ring that has an identity. So that's nice. That's better. People have gone so silent since I started yapping about this, so I assume you're all just completely mesmerized by this stuff. But you can feel free to ask questions and distract me. I mean, Deepak might be upset if you distract me, but office hours are made for distractions. So, so in particular, it turns out that there's a very special subgroup. I guess I'll talk about the whole thing. Do I really want to? I feel like I've gone deeper than I was planning to go. I wanted to try and quickly motivate affine Hecke algebras and then talk about their combinatorics, but we're getting deep into some like analysis on p-adic groups. Oh well, we're here. So it turns out there's a very special, each of these p-adic groups has a very special compact open. And it's special for a lot of reasons. So, I guess before I talk about that, you're waiting to find out what they are. Okay. Well, there's like 10 different definitions. Sometimes you define it in terms of a root system. Sometimes you define it in terms of a group. We're very close to the group definition, I guess. But the root system definition will bring us more insight into rigorous computations with them. So, all of these algebraic groups have special subgroups called, there's parabolics. So there's parabolics, and there's Levy subgroups. So Levy subgroups I've talked about before, right? For GLN, a Levy subgroup is just a subgroup where you put a bunch of copies of smaller GLNs down the diagonal. Is the DG term appearing in the integral written above something like Haar measure? Yes, exactly. It is the Haar measure. The group isn't infinite dimensional. But it is, I mean, it does have infinitely many elements in it. But the group is definitely not infinite dimensional. But you're absolutely right. So every locally compact group admits a special measure called the Haar measure, unique up to scaling. And actually, we're going to talk about there's sort of two very natural choices of scaling that we take to normalize our Haar measure. So this game of levies gets repeated for all of these other groups, though. I mean, it's slightly more, and I do mean slightly more complicated for like these other algebraic groups. But it's basically the same idea. You have levies, you have parabolics, exceptional groups too. Let's talk about those. And and the parabolics are some sort of extension. You basically sort of like fill in the blanks on the upper for the matrix groups. This is a little vague and imprecise, but you basically fill in the blanks in the upper triangle, and that's what gives you your parabolic subgroups. The sort of, I don't want to say most important, but a very important example of this is the Borel subgroup. So technically, I'm assuming here that my groups are quasi-split. Don't worry about what that means. I mean, basically, it just means that there is a Borel subgroup. So Borel subgroup is a minimal parabolic. So that is, in particular, it's a group where your, for GLN, the Levy subgroup, the corresponding Levy subgroup is just a torus. Right? It's just the diagonal matrices. And we already saw, actually, this was super important in building up the definition of our theorems to capture irreducible representations of GLN in terms of multi-segments. This played an important role. So for GLN, the Borel subgroup is just all upper triangular matrices. But there's also a version of this for all of these other groups, and it's equally as important in all of these other contexts. So, now, also, in general, things just tend to be nicer for compact subgroups. And a general theme in representation theory is you basically take a maximal compact subgroup because, you know, the theory is just easier for compact stuff, and a maximal compact subgroup is going to basically be like the closest compact approximation to your group, right? And the idea is that maybe if you by like restricting and inducing representations between these two, maybe you can leverage your knowledge about compact subgroups to learn things about G. Well, in QP, for example, ZP is a nice maximal compact open. And this is true if we adorn it with X's. And in fact, it continues to be true if we just plug ZP into, say, like any of these matrix groups. Okay, E6, G2 aren't really matrix groups, but so for example, K being GLN valued in ZP, this is a maximal compact. Okay, so well, it's a maximal compact, and not only that, but it has like a Gödel given maximal ideal, right? It's got this. It's a local ring, has the special maximal ideal, and so that means that we get. Let me erase some stuff here. Draw. Not responding. So we have this special maximal ideal, and that means that we get a quotient, right? So we have a quotient, ZP mod this maximal ideal is isomorphic to FP. And so you can take these matrices, and just reducing modulo this maximal ideal, you get a surjection onto this finite group, GLNFP. And so we have this one maximal compact. It's important. Now, one thing we do with the GLNFP, this is actually a really important source for an important and mysterious class of representations called supercuspidal representations, which I've black boxed for most of my PhD, largely, but they are very important in the theory. And one of the ideas, one of the ways that we build them is there's a notion for supercuspidal for finite groups. And one way that we can build them for our p-adic groups is we basically take it on the finite group, pull it back through this surjection. Now it's on this compact group, and then we induce up to the large group, and we know that our supercuspidal we'll have a supercuspidal representation of the larger group living in there. So this is one process by which we can produce supercuspidal representations. Someone asked you the other day what the most cited pure math paper is, and you didn't know. Interesting. That's a very interesting question. So I'm sure the suspense is killing Deepak because we're asymptotically approaching Hecke algebras here. But most cited pure math paper. Huh. Fuzzy sets? Really? Oh, Shannon. Yeah, that would make sense. That would track for sure. Mathematical theory of communication. 71,000 citations. I mean, that tracks because it's I mean, people, I haven't really read it, but yeah, I've heard a lot of people talking about how it's a really well-written paper. Also, it's super important and has gone on to inspire a bunch of pure and applied mathematics. So finite Hecke algebras are quotients of braid group algebras. Representation of braid groups yield not invariants like the Jones. Yeah, that's true, but I'm not talking about finite Hecke algebras. But this is what I'm saying. There's a problem with way too many names of Hecke algebras. Except actually, the finite Hecke algebras are super related to stuff I'm about to talk about, and they kind of, in a sense, live inside the Hecke algebras, the affine Hecke algebras I want to talk about. Well, I don't know anything about the Yang-Baxter equation, so unfortunately I can't help you there. But we're almost at affine Hecke algebras. According to a list in this article, yeah, somehow I find this unbelievable. Google Scholars count. Yeah, I just have a hard time imagining fuzzy sets would have been fuzzy set theory is that cited. There's no way. Yeah, and it also lists mathematical theory of communication. Yeah, it's probably Claude Shannon. Okay, so I said something about supercuspidal representation. So, in particular, though, part of what we do, oh, congratulations. I'm glad you made it to office hours. We take, so I mentioned these Borel subgroups earlier. Well, they also, I mean, this exists for any of these matrix groups over any field. Well, if it's quasi-split, I mean, that's the definition of quasi-split. So we take, what we do instead is now, well, not instead, but we look at the Borel subgroup. So call this is the quotient map, pi. We look at the Borel subgroup in GLN, and then what we do is we define, so the Iwahori subgroup. I is the inverse image. Well, there's other, like, more technical, crazy ways to define it, but the Iwahori subgroup can be realized as the inverse image of the Borel subgroup in GLN. pulled back through this projection map. So, for example, in GL2, it's going to look something like you're basically going to have entries in ZP, entries in ZP, entries in ZP, and then this will be something of the form P times ZP. So it'll be something like this, which is invertible. And so the Iwahori subgroup, so it's by definition, basically it's not maximal. It's a subgroup itself of K, but it is also compact and open. Compact and open. And it turns out there's the representations. So if we look at so by what I said before, we can study reps. Maybe call it superscript I. So these are representations generated by their I fixed points. This category will be equivalent to HGI modules. And this algebra is called the Iwahori-Hecke algebra. But it is isomorphic. This could be taken as one possible definition. This is an affine Hecke algebra. So right now its definition is very abstract, but affine Hecke algebras have like a well understood definition in terms of generators and relations. So maybe I'll yap about that tomorrow or something. But so this is a sort of first pass at an inspiration for why these things should matter to me. And somehow this collection of representations is kind of like the most fundamental in the category. So this is sometimes also called the principal block. Well, the other representations are very important as well, but for example, so as a very high level explanation, I mean one cares about automorphic representations. And whatever the hell that is, they decompose, say, over for the adels of Q, they decompose as some sort of infinite tensor product where you have a representation 1 over the real points of your group, and the rest are representations over the QP points of your group, Q2 and so on. And it turns out that, whatever the hell an automorphic representation is, it turns out that when you write this down, so almost all, so meaning precisely all but finitely many of these terms, almost all pi sub p are in representations, your I, maybe I'll call it I sub p because it's the Iwahori for GQP. Almost all of those representations are going to be generated by that. Actually, something's even stronger. Something's even stronger. They're actually going to be in rep K for the maximal compact. Almost all are in here actually, so that's an even stronger thing, right? Because this is a subgroup, so it's actually a much stronger thing. But so this is so really this is the one that's like very fundamental to automorphic representations, but somehow there's not very many of these representations in some sense, and these play, the representations here play a very important role. So this somewhat moderate increasing of this category to the I fixed points, really does capture a lot. And so, for example, This isn't true for all groups, but for example, if you want to study, if we want to study the representations of GLN QP, it actually turns out that this category breaks up into a direct sum of smaller categories. And each of these categories, it turns out that for each of these categories, there exists some m less than or equal to n, such that this category is equivalent to the category of modules over this smaller Iwahori-Hecke algebra. So basically, the point is that for GLN, literally everything is captured by affine Hecke algebras, but just possibly for smaller GLNs. This is not true more generally, but so this goes back to what I was saying a number of office hours ago when I was talking about how I was lying a little bit with the multi-segment description, because mostly the description I gave you for the multi-segment thing comes down to the modules for those representations generated by their Iwahori fixed components. But now, because of this theorem, you can see that actually it suffices to just study these to understand all the representations of GLN. You're back. When I get a minute, can I give my thoughts on Lasserre hierarchy? I cannot, because I have no idea what that is. And SOS programming. I also don't know what that is, so sorry. It's an extraordinary bit of math you recently came across, lots of connections. Not to distract from your current topic. Apologies in advance. No need to apologize. We're all about getting distracted in these office hours. But yeah, unfortunately, I know absolutely nothing about it. My coffee is almost done, so I am going to leave soon. So I say, but I will look this up. Lasserre hierarchy. The Lasserre hierarchy. Equivalently sum of squares hierarchy. Isn't my coffee finished? Almost. Now it's done. You might be wrong, but you think there's another open compact with special name like Iwahori. Well, I'm pretty sure the one I said is the Iwahori. I think there's only one. Well, I mean, technically, okay, technically the Iwahoris are like you have like whole conjugacy classes of these. And actually, you need to do a little bit more stuff for. There's some thing going on with like to make this more rigorous. You need like Bruja Tits buildings, and like because technically I've been very sloppy. Like these are like algebraic groups, and we're really talking about like the R points of these groups. So really we should be using some sort of functor of perspective or functor of points perspective. Yeah, Nerdy Quagsire is right. Usually around 8 a.m. I'll sometimes go as early as 7 or as late as 9, but generally between 8 and 9 you can catch me. Thursdays Thursdays it hasn't been, but I'm going to start now that I don't have to be anywhere on Thursday mornings anymore. I had teaching duties, but I don't have them for the spring semester. So I'll probably be doing every day of the week soon. Yeah. But also you can, I think if you're subbed, then you can turn on notifications. You can go to your notification settings so that it lets you know when I'm streaming. You mean there's another open compact named after someone? Oh, Oh, interesting. I mean, there's also parahoric open compacts, um, but that's not someone. But maybe you're right. Yeah, I don't know. Maybe there isn't a. Well, I mean, in my whole studies, I've never come across another. I don't think I've come across another special open compact named after someone. But that isn't to say that doesn't exist. So what are these? I don't understand. What is this Lasser thing? Uh, the Lasser hierarchy is a systematic procedure to strengthen a relaxation for an optimization problem by adding variables and SDP constraints. Yeah, this is far out of my wheelhouse. Far out of my wheelhouse. Although I did have a graph theory course where we did some like basic stuff about proving things about NP problems. I think that's gonna do it for today. My coffee's gone. I've got theorems to prove. I've got marking to do. But then I can get back as soon as I finish all of that. Hopefully by like Monday night, Tuesday morning, I can finally get back to focusing completely on proving theorems. So thanks for joining me, everyone. It's time for you to go prove some theorems. So